So today we'll be covering electric fields. So far, we've covered Coulomb's law, we've covered Ohm's law, but electric fields is a clear distinction and a clear building on the Coulomb's law that we considered in the last video. So have you ever rubbed your head on a balloon and watched it stick to a wall, or seen a tiny spark on a doorknob? So this is exactly where electric fields come into play, and these are electric fields in real life. So today we will cover different definitions, some visual representations, equations, and finally some examples of what electric fields actually are and put them to actionable use such that we can use them to develop different devices or even understand them within our daily lives. So let's get moving. So let's first understand what is the definition of the electric field. An electric field is a region around a charged object where another charge experiences a force. So it is a region around a charge object where another charge experiences a force. The main equation that we're really going to look for when we look at electric fields is the equation E equals F over Q, where E is going to be the electric field, F is going to be a force, and Q will be the charge. Therefore, what this really means is that electric field is going to be a force over unit charge, meaning that the units are going to be newtons over coulombs. As such, force is measured in newtons and Q is measured in coulombs as we measured or as we've seen through Coulomb's law. What's really interesting is that electric fields are very similar to gravity and how Earth or really all objects have gravity. If we look at gravity and the equation for gravity, we can say that is something like G is going to be the force that an object impacts on another object over the mass of the actual object. So all of these lines here, as we've drawn for Earth, are going to be the force of gravity acting from other objects onto Earth and vice versa, because all forces are equal and opposite. Charges are exactly similar in this sort of way. Suppose that we have a positive charge of +1 microcoulomb here. This charge is also going to have an electric field similar to a gravitational field. That electric field is going to go radially out from the charge. And this is exactly the sort of concept that we need to measure and use when we're designing different devices or really looking at it in our everyday lives. So let's dive a little bit deeper into these electric field lines and really understand what they really are. All electric field lines are going to go radially outward from either positive or negative charge. Let's say that we have this positive charge right here in the bottom right. All charges or all electric fields from a positive charge are going to be radially outward in every single direction. So whether you're situated and you're taking measurements at a point somewhere here, the electric field solely from that point, this point right here, is going to be outwards from the positive charge. Similarly, let's look at it for the negative charge. This negative charge is actually going to act very similar to how Earth acted in our previous example. All the electric field lines are going to be going into the electric field or into the negative charge. As always, they're going to be radially in all single directions. So let's say if we're situated at a point right up here, this point right here. If we take a measurement strictly from the negatively charged ion or the negatively charged particle, the electric field at that point is going to be pointed directly towards the negative charge. So these are some basic rules, and let's actually get them down on paper now. So for positive charges, E field lines are outwards. Similarly, for negative charges, the field lines are inwards. Electric field charges or electric field lines are always radially in or out from the charge. And finally, if we have multiple charges such that we have right here, these electric field lines can never ever cross with each other. So E field lines never cross. So here's point number 1, 2, 3, and 4. So these are the 4 points that we always have to look at, especially when we're solving some problems with electric fields. And this is exactly what we're going to do now. Let's take a look at a couple of examples and see how electric fields really act when it comes to situations such as these. So in this example, we have a +3 microcoulomb charge, and we need to find the electric field away from that charge at a point 2 meters directly to the right or directly 2 meters away. So what do we specifically know in this question? We know that the electric field is going to be outwards, since we know that this is a positive charge. So that electric field line is going to act either up or this way, some sort of radial direction it's going to act. What we can do in this case is we can use a formula that we haven't exhibited yet. We haven't used the equation E equals K Q over R square. This is the formula that we're going to use in this situation, where K is going to be Coulomb's constant. That is going K equals 9 times 10 to the 9th. Q is equal to the charge, and R is going to be the distance. Therefore, now that we have all of these variables, we can simply plug and chug into the equation that we need. So E is going to be 9 times 10 to the 9th multiplied by what is Q in this case. Q is going to be the +3 microcoulombs, and R in this case is going to be 2 meters. Therefore, when we simplify that and put that into our into our calculator, we get a value of 6.75 times 10 to the 3rd Newton coulombs. So this fully checks out. The value that we eventually got was something in Newton coulombs, and we now know that this electric field is going to be pointed outwards as well. So this is a very basic example of where we can really start with electric fields. Let's look at a little bit more of an in-depth example in this case. So here we have 2 charges in this case. We have a +2 charge and we have a -3 microcoulomb charge. We also know that those charges are 4 meters away from each other, and we need to find the net electric field at the midpoint between those 2 charges, which is somewhere right here. Let's call that point 2 meters, since we know that the value, or since we know that the distance between those 2 charges is 4 meters. So again, we can go about solving this problem exactly the same as we did the previous problem. We use our formula. Formula is going to be E equals KQ over R squared. This is the main thing that we're going to do, and we're going to use it twice, one for the positive charge and one for the negative charge. So let's calculate it for the positive. In this case, we have E equals 9 times 10 to the ninth multiplied by plus 2 microcoulombs over 2 meters squared. So the value of the electric field from the positive charge is going to be 4,500 newtons per Coulomb. And simply, we can do this for the negative charge as well, where we have E equals 9 times 10 to the ninth over minus 3 microcoulombs 2 meters squared. That's going to give us a value of minus 6,750 newtons per Coulomb. Now, since we know that there are two electric fields, we can simply add both of those up to get the net electric field. This is called the superposition rule of electric fields. So E net is going to be equal to E1 or E positive plus E negative. This is going to be 4,500 Newton coulombs plus a negative 6,750 Newton coulombs. That's going to be a value of minus 2,250 newtons per coulomb, which is our final answer. So in conclusion, what can we really do with electric fields? There's a couple different applications that we can use. The first and main application is going to be capacitors. Capacitors are extremely useful tools, and they really help us charge voltage or to hold hold charge at different points within a circuit, and we can use them for energy storage. Another reason or another application is lightning. Lightning in the air ionizes the air to create strong magnetic fields. Strong electric fields, sorry. And then finally, we can use them in sensors as well for detecting electric fields. So why does all of this specifically matter? We have a bunch of applications. How do we really put it all together to understand something fundamental? So electric fields explain how charges interact. And the forces between them. The force that two charged particles exert on each other is directly correlated with the sort of electric field that both of those charges are going to exhibit. So if you have a particle of any type, a positive or a negative charged particle, that particle will always have an electric field associated with it. So we've covered electric fields today. If you want more content and more tutorials on physics E&M topics, visit us at voltagelearning.com. And don't forget to like, comment, and subscribe. Until next time, we'll see you guys later.